Welcome back, everyone. In this video, we're going to start looking at Chem 10 ebook chapter 3 and looking specifically at electron spin and effective nuclear charge. The learning objectives that are listed here actually cover this video and then the next video as well. Let's begin. So the first thing to talk about is an experiment that was done by German physicists Stern and Gerlach, and this was done in 1922. And essentially what they did is they took and shot out hydrogen atoms in between two magnets. And what they saw was that the hydrogen atoms would get deflected. In about half the cases, they were deflected up towards one set of the magnets, and then in half the cases, they were deflected downwards towards the other oppositely polarized magnets. And from this, they obtained evidence that there is a magnetic property of atoms, and specifically electrons, and that spin is quantized. In other words, there are only discrete values that can be obtained. And we now refer to that as the spin quantum number. And this describes the direction of the magnetic moment of the electrons. Because it's quantized, we can only have specific values, and we refer to those as either having a spin of +1/2 or -1/2. Sometimes we hear that referred to as spin up or spin down. And this introduces our fourth and final quantum number and allows us now to talk about what's called the Pauli exclusion principle. And the Pauli exclusion principle states that no two electrons within an atom can have the same set of 4 quantum numbers. So to review, we talked about if you describe the n value, that tells us about the shell. The L value tells us the shape of the orbital. M sub L value tells us the orientation of that orbital. And then the M sub S value tells us the spin direction of the electron within that orbital. So within a given orbital, we would have to specify all 4 quantum numbers to talk about a particular electron. Because of the Pauli exclusion principle, each orbital can only have 2 electrons within it. And therefore, those 2 electrons, when they occupy the same orbital, we refer to them as being paired. When they do not occupy the same orbital, we refer to them as being unpaired. So if there's only one electron within a given orbital, we call that electron unpaired. So let's take a look at an example here. If we have an electron in the 4p subshell, and it's a 4p electron orbital, what are the quantum numbers that are possible for this electron? We know that a 4p means that our n value is 4 and our L value is 1. And since our M sub L values can range between -L and +L, then our possible values of M sub L are -1, 0, and 1. And the M sub S values can only be plus or -1/2, and either is correct because we haven't specified what's the scenario here. So we can have any of these combinations. We can have an n value of 4, L value of 0 with an M sub L of -1, 0, or 1, and then each one of those M sub L values can have 2 different combinations. So this is 2 combinations, 2 combinations, 2 combinations, a total of 6 different combinations, or 6 different sets of quantum numbers that describe an electron in a 4p orbital. And when we write out the electron configuration, or the orbital diagram rather, that would be commonly written out as this. This is our 4p orbitals, and so we could talk about an electron in any one of those positions. So we could have our M sub L value of -1, 0, or 1, and we could be talking about either the spin up or spin down scenarios. let's revisit a little bit the orbital diagrams. So we looked at the hydrogen atom and we said that because energy is only dependent upon the n value, that orbitals within a given shell are degenerate. So all of the orbitals in the third shell are the same energy, as is depicted as them being the same height here. But what happens when we start looking at elements with more than one electron? So let's first take a look at elements with single electrons but that have different number of protons. So helium, for example, has 2 protons, 2 electrons. And if we look at helium with a positive charge, it's going to follow the Bohr model. And you could quantify the energy of the electron, or the attractive interaction between the electron and the nucleus, as a function of the Rydberg constant, as a function of our nuclear charge, which is the same thing as the number of protons, and as a function of our n value. And so we see here, as the nuclear charge increases, for helium, our Z would be 2. For lithium, our Z would be 3. That the energy of that interaction is going to increase exponentially for a given energy level. Once we start looking at multi-electron atoms, however, the energies it turns out, are not dependent solely upon the energy level, the principal quantum number n. They are dependent both upon the n value and the L value. And so at this point, it is only orbitals within a subshell that are degenerate. We see a splitting of the shell, but within a subshell. So those, the orbitals of the same n and L value, they will have the same energy level, as is depicted here. And this accounts for what we call the Z effective, or the effective nuclear charge. Now, let's talk more about the effective nuclear charge. This is essentially the amount of nuclear charge that's experienced by a given electron. And so it's related to the number of protons. Remember, Z is equal to the number of protons in the nucleus. The Z effective is the perception of an electron of how many protons it feels are in the nucleus. The reason why there is a difference between the actual nuclear charge and what is felt is due to the fact that we have attractions and repulsions. So once we start looking at having multiple electrons, they will repel each other. And electrons that are closer to the nucleus end up repelling the electrons not only within that shell, but within outer shells as well. And they end up blocking the outer electrons from the nucleus in what we call shielding or screening. And so our inner, or our core electrons, will shield the outer or valence electrons. The way that I like to think about this is, imagine that you and a couple other people are sitting around a campfire. If you're sitting in the inner circle of that campfire, you're going to feel the same amount of heat that's given off as the person sitting next to you. However, if you're sitting farther away, then you feel a lower amount of heat for 2 reasons. One, because you're farther away, but also if someone is blocking you, then that's preventing you from feeling that heat. And so the analogy here is that the electrons in the core are blocking the outer electrons. And so the outer electrons feel a smaller attraction, a smaller nuclear charge. And so we can approximate the effective nuclear charge by looking at the total number of protons and what we call the screening constant. And this is approximately the number of electrons between the nucleus and the electron in question. And the reason the effective nuclear charge being different for a given electron is the reason for why the energy levels within the same shell split. We'll take a look at this graphically in just a moment. So let's take a look at the probability of finding electrons in the 2p and the 2s orbital. Remember, when we're looking at the orbitals, if we have our s orbitals centered around the nucleus, and then the p orbitals reach farther out. Because of that, there is a probability of finding the s orbitals closer to the nucleus than for the p orbitals. What that means then is that those s electrons shield the p electrons that are within the same shell. And so these, because there's a probability of finding the electrons closer to the nucleus here, these cause shielding, even of elements within, or electrons within the same shell. Therefore, the energy of the 2s electrons is lower than the energy of the 2p electrons. And this same pattern is followed by by higher level shells. So within the third shell, the s electrons are lower in energy than the p electrons, which are lower in energy than the d electrons. And that gives us our the total the total splitting that we saw earlier. We see here, as is depicted, we have increasing energy as our L quantum number increases. Okay, now let's try a practice problem. I'd like you to try this on your own first, and then come back and I will show you a solution. Welcome back. So in this case, we want to put each of the following sets in a multi-electron atom in order of increasing energy from low to high. So there's two things we want to remember, and that is for a given L value, so for orbitals that are of the same shape, that the lower the n value, the lower the energy. So n of 1 is lower in energy than n of 2, n of 3, etc. Okay? The second rule is that for a given, within a given shell, that the L value dictates energy levels. So the lower the L value, the lower the energy. Keeping that in mind, we can rank the sets. We know when looking at set number 1, the only difference is the n value, and so that would follow this first rule. And so we would say that the 2s is lower in energy than the 3s, which is lower than the 4s. For the second set, we have, we're comparing across two different aspects. We have differing n values and then differing L values. And so the 1s is lower than the 2s, but the 2s is lower than the 2p. And then within the third set, these all have the same n, different L values. And so in this case, all we're doing is looking at the change in the L values. And so that puts the 3s lower than the 3p and then lower than the 3d. That's it for this video. Thanks for watching. Have a great day.